All right, good morning, everyone. The midterms are almost graded, so we just have to finish a couple things up, and so the plan will be to return them on Monday. Homework due tonight. Next week we'll do lab 5. It's going to be a continuation of the hydraulic circuits type stuff, so there is no pre-lab number 5 to complete. But we will start tutorials again next week. Okay, so what we were talking about on Monday was a couple things. One is we talked about this relationship between resistance, voltage, and current. So the simplest possible circuit we could imagine involves a single battery and a single resistor. And if you hook them up in a circuit like was drawn up there, then current will flow, so voltage differences drive the flow of charge. And the reason is because if you have a difference in voltage, that means you have an electric field between those 2 points. And if you have an electric field and some free charge, that charge will experience force due to that electric field. If it's a positive charge, it'll move in the direction of the electric field. If it's a negative charge, it'll go in the opposite direction. In either case, that voltage difference establishes an electric field, which starts the flow of charge or current. So the relationship between resistance, voltage, and current was that the resistance of, let's say, some wire or some conductor is given by the ratio of the voltage difference across the conductor divided by the resulting current. Okay, and then we started thinking about combinations of capacitors. There was really 2 ways we could combine capacitors. In one way, we take capacitors, place them side by side, and we connect all the top plates of the capacitors together and then all the bottom plates together. That is a parallel combination. And we showed that we could represent that parallel combination as a single equivalent capacitor, where that equivalent capacitor would have a capacitance equal to the sum of all the individual ones in the parallel combination. So we actually showed that. We also talked about capacitors in series. In this case, you take capacitors and you line them up in a row, and you just hook them up so that, say, the left plate of capacitor 2 is connected to, sorry, the left plate of capacitor 2, yes, is connected to the right plate of capacitor 1, and so on down the line. That was a series combination. We could again represent that series combination as a single equivalent capacitance, but this time 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3, and so on. So it's the inverse of the series capacitors add up to give the inverse of the equivalent capacitance. So we haven't showed this result, and so that's what I want to start with today. So let's do our little proof of this result. Okay, so what we're going to do is we're going to imagine some capacitors in series. And we'll have a battery supplying some voltage delta V. And then we'll start with our capacitors in series. Maybe we'll draw 3 of them. It doesn't really matter. This argument we could generalize to any number of capacitors. I'm going to put a little switch in here. We'll call that switch S. Here's the positive terminal and the negative terminals of the battery. And we'll call these capacitors C1, C2, and C3. Okay, so what I want to imagine is that we start with all of our capacitors uncharged and the switch is open. So that's our starting point. So we start with uncharged capacitors and the switch S open. Okay, so one thing I want to recognize before we think about what happens when the switch closes is that we have the left and right-hand plates of neighboring capacitors connected together. And so this red highlighted section is all one single conductor, and likewise, I could say this blue section is also one isolated conductor. I say isolated because capacitors are just these parallel plates, and so they're not actually connected physically to each other. There's no direct contact between them. And if these capacitors are all initially uncharged so that there's no excess charge on any of these plates, then the thing that I colored red and the thing that I colored blue are neutral. And they always have to be neutral, even after I close the switch, because there's no direct contact between them and the battery. So there's no way that I could transfer charge directly onto these red and blue conductors. So let's make that observation. So the conductors highlighted red and blue are neutral and they're isolated from the rest of the circuit. So when the switch S is closed, the red and blue conductors must remain overall neutral. Okay, so I want to keep that in mind as we think about this. So we are going to close the switch. The battery is going to cause the transfer of some charge, but those red and blue conductors will always be a total charge of 0. Okay, so if we do close the switch, what the battery is going to do is it's going to cause the flow of charge from the negative to positive terminal. And what you'd end up with is a current I that would go from the negative to the positive terminal. Remember, current is the direction of positive charge flow. What's actually happening in the circuit is that an electron from the left-hand plate of C1 would be pulled off. It would go around the circuit in the counterclockwise direction and be deposited on the right-hand plate of C3. And that will continue. And so we'll accumulate a positive charge on the left plate of C1 and a negative charge on the right plate of C3. Okay, so when the switch is closed, the battery causes charge to transfer from, let's say, well, okay, we'll take negative charge from the right plate, sorry, positive charge from the right plate of C3 to the left plate of C1. Okay, so what we know is going to happen is we'll start getting some positive charge over here, and we'll start getting some negative charge over here. So we'll put minus Q over here, we'll put plus Q over here. Okay, fine, fair enough. If we start putting positive charge, let's say on the left plate of C1, that's very close to its right-hand plate. And so that red conductor is neutral, but it has electrons that are mobile, that can move around. Those electrons will be attracted to the positive plate. And so we'll end up getting some electrons attracted over to this positive plate. But because the red conductor has to stay neutral, that leaves excess positive charge on the right-hand plate. And so we end up getting positive charge over here. And it turns out that the amount of charge that we get on each of these plates is exactly the same. So over here, we'd have a charge minus Q, and we'd end up with a charge plus Q. The same thing happens for the blue conductor. The blue conductor sees all this negative charge accumulate on its right-hand plate. That repels electrons in the blue conductor, so they move towards the left, and so we'd get some negative charge over here, and that's going to leave behind excess positive charge on the right. So we'd end up also with plus Q here and minus Q here. So one result of a series combination of capacitors is that every capacitor carries the same charge, plus or minus Q. Okay. All right, so the neutral conductors, which are the red and blue ones, red and blue, they're still neutral, but they become polarized. Remember, we use this term polarized right at the beginning of term, and that just means that there's some separation of charge. So if you add up all the charge on any one of either the red or blue conductor, it's always zero, but we could have our negative charge over on one side and our positive charge over on the opposite side. So they become polarized. So there's a separation of charge. Okay, and the result is that each of the series capacitors carry the same charge. So if we wanted to describe the charge of C1, it would be the same as the charge on C2, which is the same as the charge on C3, and we could just call that Q. So I wrote it as a positive Q, but one plate is plus Q, and then the other one is at minus Q. Okay, good. So there's one other thing that we have to realize to help us finish analyzing this problem. So I'm going to redraw the exact same circuit. We had a battery supplying delta V, and then we have this combination of capacitors. And so C1, C2, C3. We already know that they're all going to have the same charge, but there'll also be some voltage differences across these capacitors. And so what I want to imagine doing is taking a charge and having that charge complete a loop around this circuit. Before we do that, let's just remember a similar kind of thing that you talked about in Physics 111. So this is going to be a little aside. And let's talk about gravitational potential energy. So let's imagine this is the ground. Maybe we'll call this height y equals 0. And then we're going to take a point mass, and maybe it starts at some position where it's a height y initial above the ground. Okay, and then we're going to take this point mass, maybe it has mass m, and we're going to move it around in a little circle. And we're going to keep track of all the changes in potential energy as we go around this circle. So if we move mass m through a loop in a constant, let's say, gravitational field, the net change in gravitational potential energy is 0. And that's just because if we want to keep track of changes in gravitational potential energy, well, the gravitational potential energy is just mg times the height. So the change in potential energy is mg times the change in height. But if we go in a complete loop, our starting and ending positions are exactly the same. And so there is no net change in height. So for a loop, delta y equals 0. And so therefore, delta u is also equal to 0. I'll put a subscript g for the gravitational potential energy. So if I take my pen and I start here, I can move it up. It temporarily gains some potential energy. I could go horizontally. There's no change in potential energy because there's no change in height. I bring it back down and I complete my loop. Now I'm back at the same height, and any potential energy that I gained in part of the loop is somewhere lost in another part, and so there's no change in potential energy. So what we want to do is we want to come up with something similar for our electrical potential energy. So remember, the potential energy of a charge moving through some electric potential was U was equal to Q times V. So let's now consider a charge, we'll call it little q, moving around a circuit. Okay, so every time the circuit has a change in potential, or the change in voltage, if you like, so if I take my charge across a battery, let's say I go from the negative terminal to the positive terminal of the battery of my charge Q. It's going to gain potential delta V, and its change in potential energy will be Q times delta V. So every time the circuit has a change in potential or voltage delta V, the corresponding change in the potential energy of the charge is delta U is equal to Q delta V. Okay, fair enough. So let's go back to our circuit, and let's say that we're going to take our charge Q and we're going to move it along this path, and we'll go clockwise around this circuit. And so Q is going to follow this clockwise path. And so we'll call this our initial position, and it also ends up being our final position. So if we take our charge back to its starting point, then it must have no net change in potential energy because it's back to where its initial conditions were, to whatever those initial conditions were. So if we start in, let's say, the lower left corner of the circuit and go around, let's say, clockwise, we can track the changes in the potential energy of Q. Okay, so there's a few things that are going to happen. The first thing that will happen is we cross the battery from the negative to positive terminal. And so we gain voltage delta V of the battery and potential energy of Q times delta V. Okay, so that's one change in potential energy. So let's go back now to our circuit. And so we've crossed the battery, and so now we're sitting over here. We're going to continue our clockwise journey, and we're going to come to capacitor C1. Now, capacitor C1, we already discovered, is going to have its left plate be positive and its right plate be negative. And that's true for all of the capacitors that are in the series combination. And so remember, electric potential is pointing, let's see, electric fields point from high to low potential. And so for our capacitor, the electric field would be pointing from left to right. And so that means on the left, we're at high potential, and on the right, we're at low potential. So if we cross the battery, we're going from high to low potential. The change in potential is negative. And so that means our charge loses potential energy by crossing the electric field created by the capacitor C1 in this case. Okay, so we cross C1 from the positive to the negative plate, and we lose voltage. We'll put minus delta V1. So if delta V1 is the voltage across the capacitor, when our charge goes from the positive to the negative plate, it experiences a loss of potential of minus delta V1, and potential energy minus Q delta V1. Okay, we have 3 capacitors in series, and the same thing's going to happen in every single case. So we're going to cross C2, and we lose potential energy of minus Q delta V2. We're going to cross C3. We're going to lose potential energy minus Q delta V3. And then once we've crossed that last capacitor, so our journey has taken us across all these capacitors. Then there's nothing else in the circuit except just a wire that takes us back to our starting point. And so if we're back at our starting point, the net change in potential energy must be 0. So 4 is we're now back at our starting point. The net change in potential energy of our charge Q must be 0. That's just conservation of energy. So what we're really doing is we're applying conservation of energy right now. Okay, well, let's just add up all these changes in potential that we tracked, and we'll just force it to be 0. So delta U net is equal to, well, first we gained Q delta V from the battery. And then we had minus Q delta V1 from C1, and minus Q delta V2 from C2, and minus Q delta V3 from C3. And our conservation of energy says that all of that must just be equal to 0. But if you look at this, every single term in our expression involves the same factor of Q. And so we can just divide everything by Q. So we divide by Q, and then we end up with delta V minus delta V1 minus delta V2 minus delta V3 is equal to 0. And this tells us that if we keep track of all of the changes in voltage around a circuit, they must sum up to 0. Now, we've done this for a specific example of a battery and 3 capacitors in series, but I can do this for any circuit with any types of components, and you'll always find by the same arguments that around any closed loop in a circuit, the potentials must sum, the changes in potential must sum to 0. So in general, for any closed loop in a circuit, the net change in voltage around the loop must be 0. This has a name. This is called the Kirchhoff voltage loop rule. And it is a cornerstone of all of the circuit analysis that we're going to do. There will end up being a second Kirchhoff rule, and we'll come to that probably next week sometime. Okay, so for our capacitor example then, what we have is delta V of the battery must be equal to delta V1 of capacitor 1 plus delta V2 plus delta V3. So this is for our series capacitor example. All right, so now we know two things about our series combination of capacitors. And they're both important. One is that all of the capacitors have the same charge. And two is this loop rule says that the sum of the voltages across the capacitor have to be equal to the voltage provided by the battery. Okay, so for capacitors, we know that C is Q over delta V. All right. I've got an expression here, let's call it equation 1, in terms of all these voltages. And so I could express the voltage of a capacitor is, let's see, Q over C, so for a capacitor. Okay, so specifically then, let's see, delta V1 is going to be Q1 over C1. Delta V2 is going to be Q2 over C2. Delta V3 will be Q3 over C3. And all we'll do is we'll make the substitutions and we'll put in these expressions for our capacitor voltages, okay? So subbing into 1, we would get delta V is equal to, let's see, Q1 over C1 plus Q2 over C2 plus Q3 over C3. Okay, so we're very close to where we want to be. The last step is to say, all right, we have a series combination of capacitors. I'd like to represent that using a single equivalent capacitor. So equivalent capacitor. So the idea is we'll start with our original circuit. 3 capacitors in series. There's our battery, C1, C2, C3. And we want this now to be represented by a single equivalent capacitor. Let's say C equivalent, and here's delta V. So if our capacitor is really going to be equivalent, it must charge to the same value of Q when it's connected to the same battery, delta V. So we require that Q equivalent be equal to Q1, equal to Q2, equal to Q3, which is just all going to be defined to be Q, some charge. So therefore, it must be that Q equivalent, which is equal to, let's see, it would be C equivalent to delta V, or delta V is equal to Q equivalent over C equivalent. And the last step is to make that substitution, and then recognizing that all the charges have to be the same. Q equivalent is equal to Q1 is equal to Q2 is equal to Q3 is all just equal to Q, leaves us with Q over C equivalent is equal to Q over C1 plus Q over C2 plus Q over C3. Every single term in this expression has the same factor of Q, and so we could cancel that out. I guess we'd be left with a bunch of factors of 1, right? So these all become 1 when we divide out the Q, and so our series combination of capacitors follows the rule that 1 over Q equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And so there we go. So that is our expression for combinations of capacitors in series. Okay, is there any questions about this exactly? Yep. Oh, sorry. Yep. You are correct. Thank you. Anything else? Yeah. Okay, good. So, the other thing we can do is we can start to think about, what do I want to do? Okay, let's start to think about circuits that involve combinations of resistors and capacitors. So far, we've thought about some simple circuits that have only capacitors. So we had the series combination and the parallel combination. And now we've thought about circuits that involve only batteries and resistors, and we found that the current that you get is just the voltage of the battery divided by the resistance. So what I'd like to do is to think about, what if we had a circuit that had a battery, a resistor, and a capacitor? So let's talk about our RC circuit. So we're going to have a battery, capacitor, resistor, and a switch. Okay, so what it'll look like is we'll put our battery over here. It'll provide a voltage delta V. Let's put our switch over here. We'll call that S. And then we'll have our resistor. And we'll have our capacitor like so. And this is C. So what I want to think about is we know that if we close the switch, our capacitor will charge up. So what I'm going to be interested in is how long does it take to charge up, and how does the charge on the capacitor evolve over time? So if C is initially uncharged and the switch S is closed, let's say at time t equals 0. So we call t equals 0 the time we close the switch. So what we can imagine doing is we close the switch, and at the same time we start a stopwatch, which counts how much time has gone past, and we monitor how much charge we have on the capacitor. What I'd like to ultimately do is make a plot of how that charge on the capacitor changes with time. So how do the current say I of t and the charge on the capacitor, let's say Q of t, evolve with time? Okay, um, that's actually a little bit of a tricky problem. So what we'll have to do is we'll have to start by doing our Kirchhoff voltage loop analysis that we just said. So we said that if we track all the changes in voltage around a closed circuit, they have to sum to zero. So let me label this as delta VR will be the voltage across the resistor, and delta VC will be the voltage across the capacitor. And we'll do the same kind of loop that we thought about doing for the parallel capacitors. We'll start in, let's say, the bottom left corner, and we'll take a loop, a clockwise loop around our circuit, and we'll just keep track of all the changes in voltage, and those changes in voltage have to sum up to be zero. Okay, so the Kirchhoff loop rule requires, it requires that the change in voltage across the battery, and so this is going to be our battery. And now we have to think a little bit. If I go across a resistor, let's say I cross this resistor the way that I've drawn it. I'm going to go from the left to the right-hand side. Do you think you lose or gain voltage? What would your guess be? Who thinks you're going to lose voltage? Who thinks you're going to gain voltage? Nobody, and then 80% of the class has no opinion. So what would happen is we have the left side of our battery connected to the positive terminal of, the left-hand side of our resistor connected to the positive terminal of the battery. So that's a high potential side. And what we have is the opposite side is going to be connected eventually to the negative terminal. I know it has to go through the capacitor, but it eventually leads to the negative terminal. And so what we have is the low potential. Sorry, I got that wrong. This is the positive side, is the high potential side. And then over here, we have the low potential side. And so what we're going to do is when we take our clockwise path and cross the battery, we're going to go from high to low potential. So we're going to lose voltage. And so this would be minus the voltage lost by the resistor. Our capacitor, when the switch is closed, will start to accumulate positive charge on the plate that's closest to the positive terminal of the battery and negative charge on the plate that's closest to the negative terminal. And so again, when we cross the capacitor, we go from the positive high potential side to the negative low potential side. And so we're going to lose the voltage across the capacitor. And the loop rule says that those things have to sum up to be zero. Okay, fair enough. Now, what we know about our battery, about our resistor, is that we have this relationship between voltage, current, and resistance for our resistor. The voltage across our resistor is going to be the current times R. Okay, and the voltage across, so C is Q over delta V, so delta V is Q divided by C. The voltage across our capacitor is Q divided by C. Okay, so we'll sub this in for the resistor, we'll sub this in for the capacitor, and what we'll end up with is the voltage supplied by the battery minus I times R, the voltage across the resistor, minus Q over C, the voltage across the capacitor, has to sum up to be zero. Okay, so this is the relationship between the current and the charge in our, what I'm going to call an RC circuit, our circuit involving a single resistor and a single capacitor. Okay, well, how are we going to go any further? Well, one thing we could do is we could recognize that charge and current are related to one another. So recall that current was the change in charge per unit time interval. So if we have in our circuit like some little surface and we just count how much charge crosses that surface in a time delta t, and then we take that charge across the surface divided by the delta t, that tells us what the current is at that moment. And so therefore we would have that delta V. Let's move the other terms over to the right-hand side. We'll get rid of the negative signs. Would be equal to, let's see, I is going to be delta Q over delta T. We still have to multiply by the resistance. And then we have plus Q over C. Okay. So this expression can be used to determine how the charge changes with time. We'll do the calculation next time on Monday, but let's think about what would happen. Let me draw the circuit one more time. And so let's see, we're going to have our resistor and our capacitor. Let's just imagine that we take our switch S, we close it at time t equals 0, and we watch the charge across the capacitor. So if the switch is just closed, delta V across the capacitor is equal to 0 because it was initially uncharged. So if there's no voltage across the capacitor, the battery voltage is delta V. That has to be, that's constant all the time. It never changes. What would the voltage across the resistor have to be by Kirchhoff's loop rule? Loop rule says the total voltage around the circuit has to be 0. Battery supplies delta V. The capacitor has no voltage. So what's the voltage across the resistor? Yeah. Negative delta V. I don't care so much about the negative sign right now, but it has the full voltage of the battery. And we know that delta V across the resistor is equal to I times R. So the current is the voltage across the battery divided by the resistor, and the voltage across the battery is the full voltage, the voltage across the resistor is the full voltage of the battery. And so we get a large current initially. So initially, the voltage across the resistor is equal to the voltage across the battery. So this is just that time t equals 0 when the capacitor is uncharged. And so therefore, IR is just equal to delta V. And so I is equal to delta V over R. And so this is a large current. So initially what we have is, if we were to plot the current as a function of time, we would say at t equals 0, the current is the full battery voltage divided by R. And then if we plot the charge on the capacitor as a function of time, we said initially our capacitor is just uncharged. So that's the starting point. Okay, so now let's think for a moment. We now have a relatively large current. So we have a large flow of charge. That means we're going to be depositing positive charge on the top plate of the capacitor, and we're going to be taking that positive charge from the bottom plate, so the bottom plate ends up being negative. Okay, so if we wait a short time later, now our capacitor has accumulated a little bit of charge. And if it has a little bit of charge, that means there's a voltage difference across it. If there's a voltage difference across the capacitor, then by the loop rule, the voltage across the resistor must have decreased a little bit. And if the voltage across the resistor decreases a little bit, so does the current. And so the rate that we're adding charge onto the capacitor decreases as time evolves. So as the charge builds up, the rate of charge flow decreases. So after, let's see, we have 3 minutes left, which is a good amount of time. So after a short time, delta t, our capacitor accumulates some charge. And so the amount of charge that it would accumulate is just the current times delta t. So whatever the current happened to be, times however long we waited, that's how much charge gets deposited on our capacitor. So now the voltage delta VC across the capacitor is non-zero. So therefore, the voltage across the resistor and the current decrease. Okay, so on our plot, what we would say is, okay, we've added a bit of charge to our capacitor if we wait a certain amount of time, delta t, and because of that increase of charge across the capacitor, our current will go down a little bit. And then we wait another amount of time, delta t, and during that time, we accumulate more charge on the capacitor. Okay, but the current went down a little bit, so the amount of charge we get is a little bit less. So I'm going to step up a smaller increment. But as I put that extra charge on the capacitor, its voltage increases across the capacitor. Therefore, the voltage across the resistor decreases. I is the resistor voltage divided by R. But if the resistor voltage went down, so did the current. And so the current decreases. And this will keep happening over and over again. And so every time we get a little bit less charge on our capacitor and a little bit less current in our circuit, and eventually the capacitor ends up being fully charged. And when it's fully charged, the voltage across it no longer changes, and it ends up being exactly equal to the battery voltage. And that means there's no voltage across the resistor and the current goes to zero. Yeah.
How are you able to determine the current line?
So I drew the current line like that because I know that that's what it's going to look like, but we'll do a proper calculation on Monday. Yeah, so this current is an exponential decay is what it'll turn out to be. And then the charge will be an asymptotic approach to a constant. So I went through this argument just to show kind of roughly what we're expecting to see, and then we'll do a proper calculation on Monday. All right, so that's it. Have a good weekend. Yeah. Yeah.
Okay. Yeah. Just look for those then.
Yeah, just go to the course website and you'll find them, no problem.
Perfect. Cool.
Yeah.
Thank you.
Sweet. Yeah, see you. You too.